I'm Cameron. I'm going to walk through how we design the steering system this year. So the function of the steering system is to convert the driver's input at the steering wheel, so a torque, to lateral forces between the tire and the track in order to traverse the car along a curved track. Some of the goals that we have for this year are to pass mechanical tech inspection, to meet ergonomic needs. We set a steering effort maximum of 20 Newton meters. I think in commercial vehicles, this is between 5 and 10. So we'll be a little bit heavier, but actually we get close to that quote, but you'll see.
Where'd you come up with that number?
20 Newton meters.
Yeah.
I mean, last year's.
Oh, the driver's gone, but I just wondered if the driver can go, yeah, like this is how much.
Last year's we predicted around 9.4, and he said it felt light, so we went about twice as heavy. And then we have geometric constraints in the system. We need to traverse a 4-meter outer radius turn in the endurance event. That's the tightest corner that the car will have to go through. And then on the skid pad event, it's essentially a constant radius. The driver takes 2 laps around a left-handed and right-handed circle. It's like in a figure 8. So we want to see how close we can get to target velocities. Briefly, this is an overview of the system. The driver interacts with the steering wheel, essentially just grips that control the angular position of the steering column, or allow them to impose a torque on the steering column, which is coupled to the pinion gear in the rack and pinion mechanism. And then the rack and pinion, the ends of the rack are mechanically coupled to the upright. And this allows the car to turn when the pinion gears turn. So some takeaways from last year's car. I think the lowest hanging fruit for us in terms of just scoring higher in competition was just doing more well-documented designs. So showing where numbers came from and how we chose a certain design choice. In terms of the actual performance of the system, that is what in the bottom left, what we had CAD'd. And it ended up over constraining the column. So you would have like an increase in torque that you had to input at the wheel at certain points. So we ended up cutting off the lower support, and we constrained it with spacers on either side of the upper support. And then in terms of serviceability, this is what the CAD for the rack mount looks like, and they were welded to the front, to the bar in front of the A-arm node, the bottom right A-arm node in that picture. We ended up having to drill holes in the bottom, and it was a big mess in terms of like you would drop a nut inside of there and it would be impossible to get out. So something we wanted to keep in mind. So now I will talk about the steering geometry. So how did we place the rack in the car? This was the first geometry choice I'd made, and it was mostly due to packaging. There were issues with achieving full clearance with the hub motors. So I can't go obviously beneath that. I have to clear this chassis too, but I also can't interfere with the hub motor while the wheel travels. It's kind of like just threading a needle. So that was the main consideration in terms of the vertical position in the car. And then in terms of the X position longitudinally, this was mostly ergonomic considerations. So because it has to interface with the steering wheel, the steering wheel has to be at a certain position we got from the ergo team. And the U-joint can only achieve a certain angle. So we had to place the rack at least a certain distance from forward in the car from where the driver sits.
So one of your constraints is an existing rack and pinion assembly that you're using, right?
Yeah, the CAS rack is a very common FSAE rack, and it is, yeah, it's bad to start with that constraint, but this is I think like half of the teams that were at comp last year used it. And it's slightly heavier, but it's much more reliable than other rack assemblies.
You own this?
Yeah.
Okay.
We own one from last year, but we plan on rebuying one.
Okay, so I would have preferred. You could have stopped and I would have been satisfied, but continuing on and telling me that the reason you're using it is because everybody else uses it as a limited excuse.
Yeah.
Using it because we already own it, we have experience with it.
Yeah.
Is what I would find reasonable.
Yeah, that was mostly our design choice last year. This year, it worked last year, so we're gonna use that. Yeah.
It works and it's, you know, just. So you said it earlier, you've got to learn to present your case as to why you're doing what you're doing. You had a great answer for the 20 meters, but it just wasn't on the chart.
Yeah.
And this whole conversation, you know, concise engineering, why did we do it? How does it work? What are the numbers? Get used to telling that story succinctly.
Yeah.
Because that's sort of what they're looking for.
Yeah.
And you said it well, but get used to who we can practice it. Otherwise, when you go to do your report, you send to them, you're gonna find the same things you left out.
Yeah. Thank you.
And some of that, you can consider doing things internally, because you're getting us asking you a bunch of questions that I don't know if you do internal peer reviews, I have faith recollection, you do. Ask these same kind of questions. Where'd that number come from?
Yeah.
Why is it right? Why are you using that? Why does it work for us? Get used to always answering all those questions. Make you a lot better at writing things to past tense.
Yeah.
Just to backtrack a bit, Cameron, were there any issues that the design judges found last year or any suggestions they had for the steering system?
Yes. One of them was not just the steering system, but the suspension geometry as a whole. We had like the paper that they gave our team. They said that they didn't want our roll centers in the ground, but I don't think this was changed in this year's. They also, when we moved to manufacturing last year's design, we made compromises in how we were going to locate where the rack was, because in this, well, I haven't gotten to rack mount yet, but in this assembly, I've made it such that these surfaces are flush so that we can just fix it there. And they're also locating holes. So if there are welded inserts that the mount screws into. Last year, this member here was circular, and we had notched tubes. If I'll go back, these that parallel with that plane. But when we were originally designing the steering system, they were slightly higher, and this was to avoid bump steer. So when we moved to manufacturing, this was compromised, and the judges noted that. That was one of the things. So I've yeah, kind of getting ahead of myself. Yeah. So the other component of the steering geometry as a whole is where I place the outboard pickup point. This decides like how the wheels travel. Essentially, as I mentioned earlier, the tie rod in the unsteered position has to intersect with the instantaneous center of roll of the A-arms, or else when the suspension actuates, there will be, if one side were to actuate, you'd have a change in length between the, you would have steer in one direction in bump. So we align their roll centers, and that defines the plane of where the where this geometry sketch can exist. So the tie rod has to lay in this plane, and I'm sorry, I'll back up. This plane that contains the tie rod is the intersection of the instantaneous center of roll and where the rack inboard pickup point is in the unsteered position. So this point is found by where it intersects with the kingpin axis. Sorry. So I've tried to reduce this design problem down to the tie rod has to lie in a plane, and the moment that the steering effort force from the tie rod has about the kingpin axis to turn the wheel is defined by an angle and a distance, essentially in polar coordinates, like an r and a theta. And we decide the r and the theta. The r will be the moment arm that you have about the kingpin axis to turn the wheel, like in cornering. And the theta will control how slip changes at different actuations of the wheel. So based on where this point is around the circle of a certain radius, the wheels will travel, the inner and outer wheels in a turn will travel differently. So the 4-meter constraint, I found the outermost point on the car assembly. This is like on the front wing. So in order to not hit a cone, this distance would be 4 meters, and the steering angle necessary, if you assume slip is low enough, would be 31 degrees. So this was a minimum target that we had to achieve in this design.
What side of the wheelbase was?
This was on a route.
It's minimum by the rules plus some tolerance for manufacturing.
So can you say this again
Yeah,
in like,
I'm sorry, I was.
well, no, say it in like simple terms. It's like we had to make sure the wheel turns enough
Mhm.
that the farthest point of the car doesn't hit
Yeah.
4 meters.
Yeah.
And so you made sure that
So
the steering rack has enough travel to turn the wheel this degree or whatever.
yeah, whatever, the bicycle model is a model that's used in vehicle dynamics, where weight transfer is negligible and slip angles are small, to predict the behavior. In this drawing, it's essentially just, sorry. I'm just trying to,
Pretend like I'm 5. Explain to me like I'm 5.
if slip angles are 0, this wheel and this wheel share an instantaneous center of roll at normal to the wheels, or the direction where they're pointed, if you can neglect slip. That's what I'm trying to convey here. And so in order to satisfy this geometry where the outermost point is 4 meters away from the roll center, delta has to be 31. That's what I was trying to convey here. That's the limitation on our design.
In layman's terms, what is the turning radius? Is it 4 meters?
So that's in the rules, they call it just like the outer radius turn of 4 meters. In vehicle dynamics, you'll see it compared to the center of gravity of the vehicle.
Okay.
Yeah.
So in layman's terms.
Yeah.
So I know you're talking about turning radius. What's the number?
So lock to lock,
Yeah,
31 degrees out, straight, 31 degrees the other way.
yeah. So in this,
In order to,
it would be the average of the two wheels because they don't necessarily travel parallel to each other.
right.
That's what I was trying to convey in this drawing here. So this is the calculation for estimated steering efforts. It's just a moment balance about the kingpin axis. So you have the lateral force, the cornering force acting at the mechanical trail behind where the kingpin axis intersects with the ground. And the self-aligning torque of the wheel. This came from the tire testing consortium, which provides tire data at certain cornering conditions.
Is that caster? Self-volume torque?
Yeah,
And
Well-
that trail, okay, essentially caster.
mechanical trail is caster. Yeah, the self-aligning torque is a property of the tires.
Right.
Yeah. It's the tire's response, the rubber's response to deformation of the contact patch. Yeah. It's empirical, which is why we had to refer to the TTC. Yeah. So this placed a lower bound on the steering arm for us. So it has to be at least 1.56 inches to reach the torque, to reach the torque targets we set out in the beginning.
Is it a typo that it says 1.5 Gs here rather than 1.6, as it says in the other slides?
No, I thought it was 1.5 we were aiming for.
The 1.6 number came from ordering maximum towing loads that the tires can handle. So I think that might be, if you want to work at the maximum limit of what the tires can do, it might be a better
Yeah.
number.
Steering arm, in this case, is the travel of what is 1.56 on the diagram?
1.56 would be the distance, the smallest distance between that orange line and the force in the tie rod. That would be essentially your lever arm over that axis.
Right, okay.
Yeah. So now we have like, I'm trying to like, you have a plane in which the tie rod must exist at unsteered.
Yeah.
You have a point and a radius that this point has to lie on, or a minimum radius that this point has to lie on. And now I'll move to how we chose the angle. So this is the tire data for this is I fit lines to the TTC data that I mentioned earlier. And we can see that for higher loads, the slip angle occurs slightly farther out. So in load transfer, we want to turn the outer wheel slightly more than the inner wheel to induce a peak at a higher slip angle at the outer wheel than the inner.
Source for this number.
These are your calculations.
This is just empirical data. I just fiddle.
There's a lab that just buys tires that a lot of FSA teams use, and they have a testing rig where they'll load the tires at these different loads and then rotate them to achieve slip angles, and they'll publish the data for some amount of money that we purchased. I think it's like $200 to buy this data. And a lot of FSA teams just use this because they trust their testing methods. So
It's a long drawn out answer for, the source is empirical data from this source. That's all I was curious about.
Oh,
I look at these and it looks like somebody did this and plotted it in Excel.
Yeah, I'm sorry, I misunderstood the question. I thought you were questioning my interpretation of this data, how we want to. Yeah, this is from a company. Yeah, this is from a.
What was this?
Yeah, okay.
In the bottom source.
Yeah, it's a tire testing manufacturer in Detroit, I think. Yeah, Calspan.
What tire compound are you using?
It's the same tires as last year.
Same as last year?
Yeah, Hoosiers.
I remember this in session, the LCO.
It's the same. Yeah. And so here on this graph, I've tried to effectively demonstrate the effect of putting this circle at different points, or putting this point at different points on the circle, how it changes how the inner and outer wheels travel. So for theta is equal to 0, you can see that they travel like near parallel, but for theta, if you move this point inboard along this circle, the outer wheel begins to travel more than the inner wheel, which is what we're aiming for. So at around 80 degrees of steer angle, that's steer at the wheel, not the front wheel, not the front wheels. We want about 3 degrees of more angular travel at the outer wheel than inner wheel. So that's what this plot was trying to demonstrate. This is for the steering arm, which we set out with in the beginning, which is it ends up being around 3 inches.
One of the things on some of these slides is there's a bunch of data, and is that your conclusion? Is that 15 degrees is what your goal is or your target is, or it might be good to be clear, like, here's the data and this is our conclusion, or this is our decision or our takeaway from this data.
Sorry, so this is a property of the geometric, or this is plotting a geometric variable, which is based on a certain point on this circle, completely ignoring tire data, the wheel hubs will travel at different, they'll have different angles at different values of travel. Based on where this point is.
So what's the takeaway?
The takeaway is that on the previous slide, we said we wanted slip to occur on the outer wheel for the higher loads at about 3 degrees more than the inner wheel, which would be the lighter with load transfer, the lighter wheels. These peaks occur about for the lighter loads at around 2 degrees and at about 3 to 4 degrees for the heavier loads. And something that might be a little bit confusing is that there aren't any peaks. This is a consequence of the way that Calspan does their tests. They use sandpaper instead of a real track, like on a conveyor belt under the tires. And so the interface between the tire and the sandpaper is much cleaner than would be on a real track. So I don't aim to design for 12 degrees of slip. We sort of bring it further back. So because we want these slip angles to be at about 3 and 5 degrees for the inner and outer wheels respectively, we choose this point to achieve those slip angles. So based on this plot, I deduced that the steering arm should be at 50 degrees with the chassis center line at the unsteered position. And this is a summary of what our steering geometry looks like this year. So our steering arm is 3.1 inches away from the kingpin axis. That's the moment arm that the rack essentially has on the kingpin axis. And then the inner and outer wheel max travels are 32 and 35. So they're both within the geometric constraint that we set out earlier to achieve the 31 degrees. And then our steering ratio is the overall ratio of steering wheel angle to travel at the front wheels. So since the pinion can turn 124 degrees, the average travel of the wheels is about 33. It ends up being around 3.6.
All said and done.
Yeah.
Looking at this, and this is great, it's a nice summary. The rack and pinion is already specified, that's a constraint.
Yeah.
Your wheelbase is a constraint, so the distance between the rack and pinion and the wheel is a constraint. What, did you have any latitude for design at all? Or did you just analyze based on the constraints that you were forced to? Because I don't see that you can really change anything, even if you wanted to.
Where the left, right, left, pin to the wheel, this track is not constrained. The
No.
track can be always never been.
Track, I mean, yeah, it was 48 inches for this year. Yeah.
I mean, it shows
Where the rack can go in which plane,
you can also move it forward and backwards.
forwards and backwards, but the way that I see it, I don't, maybe I'm looking at this wrong, but if you move it forwards and backwards, it starts hitting things.
It's mounted to these chassis bars. Do you mean forward and?
Yeah.
Yeah,
I know you can move it up and down, but.
yeah. Oh, this is a top-down view of
Right,
the
exactly.
chassis?
This is top down.
Yeah,
So
sorry.
do you have, so your really only design ability is to move the rack around.
And choose the outboard pickup point. Yeah,
Okay.
Yeah.
You have a lot of constraints. I just figure, what leeway did you have to do all of this?
yeah.
Was this just you doing analysis based on what you were stuck with? Give us
Yeah.
a little vote.
And what you were trying to do though too, was you were trying to, within that constraint space, get to the 20 Newton meters. Based on what last year's design was.
Yeah.
Feedback.
Yeah.
And is that in the summary actually? The 20 Newton meters?
No, so the torque here was So the steering arm I chose here was 1.6 around.
That results in the force being.
Yes, yes. So it ended up being about 3.1 by the end, considering packaging and FEA on the uprights.
Yeah.
And so the effective that torque in that cornering case would go down to about 10. It would about half, because this is about double the moment arm.
Okay, so you weren't able to get to the 20 then?
The 20 is a maximum constraint on the, we'd like to keep the steering efforts low for the driver's sake.
Oh, okay, sorry.
Sorry, I don't think I made
Because
that
it was
clear.
9 last year, you wanted some more.
No, sorry.
Maybe it was 15.
Yeah,
It was too easy last year, so we wanted to make it harder.
yeah.
But I agree, seeing what you eventually came up with would have been nice.
As in like a,
What the steering torque actually ended up being.
oh, I see. Yeah,
Like tie this back to
It
the
is not
original
that
bolts.
We
Yeah.
moved to this, but this is best we can.
sure.
Say a must, but what was the resulting steering torque?
About 20 Newton or 10 Newton meters, about half of the 20 that we projected earlier because we've doubled the moment arm.
That feel should be somewhat similar to last year.
Correct.
Steering torque good last year. I thought that for this good was.
And you heard a little story about when it was stiffer and take a little more with it, so.
Mainly under, like, Sam talked a little bit about deflection under like braking, so hit bump deflection. And it would kind of jerk the steering wheel one way or the other, so mainly just stiffer in that sense, but for effort, like normal effort through a corner. it was good.
Yeah, so now we'll move into the manufacturing of the system. So to mount the rack, we're gonna make these L-shaped brackets which will bolt into threaded welded inserts on the chassis. Yeah, I had FEA, but I don't know how to access.
You're gonna machine that thing from solid stock?
Yeah,
Really, machine an L bracket out of solid stock. It's not 10.
well, it's 1/4-inch steel.
Yeah, which means you're gonna have to start with, I'm just scaling this in my little brain, probably. You're gonna have to start with something that's 1.5 inches thick and cut most of their way.
Yeah, this is something that we'll have to revisit. Yeah,
Could you go back one
It's-
slide?
I'd really look for 4130 angle stock and just get some angle and chop it off.
Yeah.
How thick was it?
1/4-inch
I think it's in.
steel.
Yes, mild steel, thermoly. And steel for inch.
Okay. and
Yeah.
then That bracket on this slide,
It's inconsistent. Yeah, sorry,
which is the correct one.
this one.
Okay.
Yeah,
Is there enough adjustability so the lower constraint?
yeah. So I have aluminum spacers that go between the mounts that clasp the rack into place. So we can slightly adjust the height just by manufacturing a slightly different aluminum spacer. And then on the,
bracket.
yeah, so this guy here.
Yeah.
And then on the outboard pickup point, we have like Anirudh was showing those universal brackets. We make spacers that go between, essentially like a width mate in SolidWorks between those. So we can adjust the height slightly by changing the dimensions of those spacers.
Is there a bushing under that bracket or is it like metal to metal?
In this one,
Yeah.
it's metal to metal. It's keeping it in place. There's yeah, it has like notches. So this one, it's like female on here and male on there to keep it in place.
Figure, it's round on top. Is there matching cradles?
There is a matching cradle underneath. Yes.
Are these considered critical fasteners?
Yes, there's a nylock insert on the bottom of this.
So they consider nylons okay for positive fastening?
Yeah.
Oh,
And then it's notched to keep the rack from sliding.
Yes,
Right.
Yeah.
Okay, so back to right one, you're good.
How is it attached to the chassis?
So there's a welded, the chassis tubes here will have a hole. And then we will weld an insert inside of those holes and then it will bolt in.
So
Yeah,
the chassis tube thickness
yeah.
is like
It's sort of, it's flanged, so we were gonna weld it like around. It doesn't need to be flat. It's it has an offset in the bracket.
Oh, it's like kind of same problem. The clear the well.
Yeah. Yes.
Are you able to adjust where that guy, the U shaped holder bolts onto the rack? So
No,
are you able to
it's
slide the rack back and forth?
no. It's kind of, it's discrete. It's like you have to mount it in these notches.
So how does the tolerance work if, let's say, the chassis is
Slightly wider.
half a centimeter long?
Yeah. That's a good point.
Say about rivets, are
Um,
you allowed to rivet anything?
I'm not sure about rivets, but
You're allowed to.
Sorry.
You're allowed, you're not gonna go fast.
Oh, yes, you can't rivet this.
I was also advised last year when we made the steering rack mounting not to use rivets because it would end up spinning on us. Is what,
So you have pretty nylons on the bolts going, I guess, into the screen.
Yeah.
What about the ones into the chassis?
no, so we would have a different positive locking mechanism for those ones. Yeah,
Yeah, I really think long hard about how you're gonna tap with that rectangular tube.
It looks like the whole thing is gonna be over constraining the racks. Because the bracket has no play on the rack. And you have two brackets on either side, so any angular distance across that and any mismatch of where your holes are, just tweaking the rack
yeah.
in both axes.
Yeah.
I mean. Yeah, I guess you can't do the pushing there, this. A lot of automotive normal racks have rubber bushings to account for that, but. Front can't, because that's how you prevent side to side.
Yeah.
So those are the only two mounting points on the rack, there's not a,
Yeah, there's one on either side.
okay.
Yeah.
Not a third one in the middle.
No.
Said it's supposed to sit in a notch.
Yeah. That's the CAD that CAS gives out is very simplified.
Okay,
But
but there is a notch there.
there is a notch at this position on the rack, yeah.
Do you think you could weld that thing on the frame close enough to mount it right?
It would be. Yeah, that's a good point. I was thinking that VR3 would handle the tolerancing on that hole and the bogey in place would be, but yeah, that's it. Yeah.
If you can weld it close enough.
Yeah.
That's all the other problems. And let's just say you can't weld it close enough, then put some slots in your hole.
Yeah, if you slot those two vertical,
In this direction.
for the bracket,
Mhm.
that will help a lot.
Sorry, slot in the left to
We'll
right
need
side.
the
of
other
it.
ones. We'll just need the ones on the bottom
Yeah.
and slot those, in this direction to get it right. And then if you need to stand it off this way, you can just basically put shims in there.
Yeah,
If they can't get it back this way.
okay. So for the steering column mounting, we're using or manufacturing, we're using a similar setup to last year. We have a double U joint between the upper and lower shafts. The shaft is coupled to the pinion gear on the CAS rack using a splined coupling. the same spline, similar spline coupling is used to couple the lower shaft and the U-joint. And then at the upper shaft, we will constrain it using spacers.
You have all splines, male, female, all that.
Like in order or on hand?
Well, either spline interfaces, are those, do those exist already or do you
Yeah.
buy those? You don't-
Yeah, so the coupler, the spline coupler, which is welded onto the lower shaft, and it has a set screw that couples to the
You don't have to machine spline.
no, but we bought off the shelves. Yeah, same for the quick release assembly. So we have a weld-on hub at the upper part of the steering shaft. And this is in the interest of saving space. I mentioned earlier that we had that geometric constraint in terms of placing the wheel at a certain distance from the driver. A lot of hubs are kind of longer than this weld-on hub. So yeah, to keep the wheel from getting too close to the driver, we use a weld-on.
Oh, the wheels, a couple of these couplings are set screws, right? Did I hear that right?
Yeah,
They're splined with set screws?
yeah,
How do the wheels feel about set screws?
they're within the rules. We used, sorry?
I'm impressed. I mean, I never, ever trust set screws. I'm surprised that they let them fly.
Yeah,
Non-critical, I guess.
yeah. I guess, yeah, there's really a lot of, they're very commonly used and there's no really way to positively lock them.
Oh,
So
there's not. You're trusting friction. That's all you're doing.
yeah,
Thanks.
yeah. So that's the steering column. And now Jakob will talk about his steering wheel design.
Hello everyone, I'm Jakob. This is the steering wheel for this year's car. There aren't many rules governing the steering wheel. The two main ones are that in any of its positions, it has to be under the front hoop, and its perimeter has to be in one continuous direction. So you're an ant walking on the perimeter of the steering wheel. You can't turn one way and then turn back to the other. So it has to be continuous. From what I found online, there was an article by a previous design judge, FSC design judge, who did a study of what forces a average engineering student can put on the steering wheel. And from this, the conclusion was that the steering wheel has to withstand at least 660 newtons laterally, which is this way, and a minimum of 100 Newton meters to 135 Newton meters in torque. Though the car will likely never exceed 20 Newton meters, or maybe just a bit greater if there's a bump, I decided that it's still good to go with these numbers as a factor of safety, basically. A common thing that, yes,
Would lateral force not be side to side?
it's this way, right down this way. So you put it,
To both?
yes. Though I find it hard to imagine a driver willingly doing this.
It's like when you're turning, like you're holding on the steering wheel to kind of support yourself.
I guess it goes.
Did they have the axial force, or was it the same?
It's that.
Which is this force.
Yeah.
Oh, I hadn't thought about that. Oh. I'll take that into consideration. I can go ahead. Right, yeah. From these numbers and doing FEA on the back plate, which is we'll get into, there's an exploded view on the next slide of the steering wheel, or on the next slide of the presentation. But the back plate of the steering wheel is a 1/4 inch aluminum plate, which we'll get from Side Cut Sun. And we have a potential ERCA project for the electronics housing and the grips for resin casting them out of I decided on polyurethane casting resin, which is easy to work with and structurally sound, as well as it can endure stress over time. That's what the electronics housing will be made out of. The changes from last year are that it's smaller. Last year's was about 10.5 inches in diameter. This year's is 9. The grips should be more ergonomic this year and comfortable to hold, which we will develop through 3D printing prototypes of the grips so that they're comfortable to hold for all of the drivers.
Why is it smaller?
Just the demand from the electronics team. Request.
What are the drivers?
That's what I wanted.
So, yeah, so the steering wheel last year was pretty big in diameter compared to like the width of the chassis, so like your elbows would to like hit the sides of the like, side impact structures. So it's sort of like a smaller wheel, so like elbows would be.
Probably wanted less room for wiring and certain ports.
There's not much that goes in. There's the display that will purchase it so that it already has a microcontroller on the back of it. The buttons will wire to the display. If you could go to the next slide, please. And all of those wires will go to pass through in the quick release. So last year we had a wire coming out from the side of the steering wheel and that connected to the dash of the car. This year, the electronics team requested that when you take off the steering wheel, there shouldn't be anything on it. So all the wires will go through the center of the steering wheel backplate and into here, which has spring-loaded contact pins that connect to the other half of the electronics assembly. So there's two PCBs. One has the like copper strings with electrical connection to a wire, and the other side has the spring-loaded pins that mount to it, not press against it.
What kind of signals are going to do that?
Digital. So that's what the microcontroller takes care of.
Power, ground, and high camera.
Okay, so different focus. And have you done that before? And do you know like what kind of PCB call for plating and surface materials and stuff? And a good reference for that?
For that, for the quick release interface?
For the wipe surface.
So the wiping surface is just to make sure that, because like when it's fully attached, like the quick release is attached to the car, it won't be spinning.
Okay.
Those are stationary.
It's not a rotary.
Yeah, yeah, it's just to make sure that like if the steering wheel isn't aligned and it's spinning, then it won't like short anything or.
So as the wheel turns, the contacts are back.
Yeah.
Okay.
To attach the steering wheel to the, so there's two parts to the quick release
Right.
mechanism. There's the hub and this thing, and to mount it, you need to twist it on. So.
Okay, so that, yeah, along this scary.
So you have I'm still bundled there on the steering wheel size, not totally convinced. I mean, because I get, depending on how far out it is, your elbows might get, then I also worry when it's too small, it just starts
It's hard
to
to
feel like an odd motion for your arms. So I'm thinking back to the mock-up we saw from the ergonomics people. Can you do a quick prototype with steering wheel and make sure the drivers really do like the distance and the size?
Yeah, so that's part of what the 3D printing will be for us, the
Okay.
rocket prototyping.
And was that wheel size factored into the steering force
Yeah.
calculation?
Right.
I missed that.
Yeah.
Yeah, it was.
Yeah.
The 9-inch versus last year, 10.
The 9-inch versus 10-inch hasn't been done yet. We will do
I mean, I think this question is relative.
Oh,
So
Steering torques,
Right,
you know,
yeah,
you don't
steering
have a lever arm, so.
the lever arm was in reference to that. In terms of calculating the torque at the steering wheel, this was dependent on the radius of the pinion and the radius of the steering arm. This was not, yeah,
So it's just the torque right there at the center, which is not that.
Exactly.
Driver's experience.
okay.
So I'd sort of like to make sure we know what the driver's.
it's
experience
kind of
is.
relevant, both the torque and the input force, depending like based on the radius of the steering wheel are relevant.
Right.
Yeah, I should have included the force factoring in the radius of Jakob's wheel. I looked at torque, yeah. That,
Aside, did we talk about tie rods
No, we did not.
Is there anything in here about that? road?
It's essentially the same as last year, except the material is switching and in terms of foresight of design, we've changed the inner pickup point to be the smaller rod end. We ended up having to change.
Switching to carbon fiber.
Yes.
Is that what's going over and tested, broken tested all?
Anirudh was, I hate to
We
pick
are
it up.
going to test them. We're waiting on some carbon fiber.
Okay, you need to make sure it doesn't buckle on those inserts and adhesives that are using to pull that.
Yeah.
Yeah.
We're gonna, we're gonna test our bonding methods along with buckling and stuff.
And then using one left hand, one right hand in
Yeah.
the rod end. And then somewhere in there, you want to incorporate two flats or a nut, so you can get a wrench in it to actually fix it.
Yeah.
Just keep that in mind. I don't, you can't find it. So, somewhere else.
And they're all adjustable turnbuckles, right?
Yeah.
Yeah.
They can be, you need at least like 3 threads of engagement in the rod end and the, so yeah, you'll have however much the length is minus 3.
Cool.
Yeah.
But the control arms are too, right? And the A arms are adjustable length.
Yeah, the A-arms are adjustable. They have the same rod ends and threaded inserts of either side, yeah.
Have you thought about how you're gonna get the wires from the spinning end of like the quick release contacts to the stationary chassis?
There will be a hole drilled in this side of this part of the quick release.
So those concentric gold circles,
No, so this is the PCB. There will be a wire from the back of this that comes out of a hole and right here.
so you're not trying to conduct electricity from something that moves to something that doesn't. So when, as the driver turns, that wire is still gonna turn.
It's still gonna turn. Yes, there will still be a dangling wire from some area of the steering wheel to the dash. It won't go through the steering
I
column.
see those things, they look like slip rings.
Yeah, it's not a slip ring.
I'm like, please don't try to design.
Pogo contact.
Bad idea.
Oh, that was.
Live with the dangling wire.
Yeah, it's just that when. There's also an egress test for getting out of the car quickly, and for that you need to take the steering wheel off and check it. So an extra step would be removing that wire, so that gets rid of that stuff as well.
Actually, they let you do the egress test when they disconnect.
Oh, okay. From the videos I saw, most drivers take the steering wheel. And...
Yeah, no, they let you disconnect the wire before you do the test.
Oh,
Because in reality, you're just gonna throw the steering wheel and it's just gonna hang.
okay, that makes sense.
Doesn't matter if you're a D-Rose though. It's in like just the wrong way.
But for their rules requirement and their tests, they allow you to have it disconnected.
That seems disingenuous, but I mean, if it.
That's their,
it's within the rules.
that's their rules requirement, and then pre-disconnected, and we can hand it off to someone, so we didn't have to throw our steering wheel.
Yeah, that sounds like, you know, you caught the judge on a good day.
I think the time requirement also was kind of strict, it was like 5 seconds. Whereas I think the flame resistance of your suit is supposed to be at 10 seconds. Or I forget exactly what the value was. So it's like there is that extra 5-second window. That's probably what they account for of you maybe like getting in the way. I don't know. Yeah. Yeah, exactly. But
Yeah, you don't have
yeah.
wire hanging.
Are there multiple points of contact for the electrical for like each signal instead of single spring there's multiple?
There's like 5.
Okay, so plenty of redundancy.
That's all we have. Thank you.
Yeah, so we're running a little behind schedule. I think we're gonna try and do a lunch break right now and then breaking after. Probably come back from lunch at 2. So we'll be about half an hour behind, or we'll be one breaking section behind schedule.
You're good. The Zoom people can hear that thing.
I'll put a message on the Zoom.
Oh, you must be good then.
Are you been? Pretty good.
There's other. Do we have is that what it is? He's not. Always. So. Oh, yeah.
There's no Diego's,
I think we're ready to begin. I don't know if Kirk will be returning or not. I don't know. I think we'll just go ahead and start. Should I do anything to the Zoom, like record or anything?
I should be recording still.
Yeah, just unmute.
Oh, it
says recording.
I don't think you need to unmute. I think the
The audio's good. Audio's good? Okay. All right, so my name is Jackson. I'll be presenting the braking system here. So just to begin, actually, before I get into the constraints, I wanted to touch a little bit on last year's braking system. I forgot to make a slide on that. But essentially, the system worked well. We were able to lock up all four wheels, which is one of the requirements. I attempted to construct a balance bar that didn't work well, and then I removed it and just used natural bias from the master cylinders, which ended up working. So I'll be kind of following the same formula this year, except kind of trying to get more off the shelf stuff than building it myself, just for time, and the cost isn't too great to just buy it off the shelf. But going into the system constraints, the rules are it has to act on all four wheels, operated by a single pedal, capable of locking all wheels, like I said. Has to be two independent hydraulic systems, and each with its own fluid reservoir. My goals are to pass the brake test, which I'll explain in the next slide. I want to supply stopping power for the entire event, because without stopping power, you basically can't drive. Well, you can drive, you just can't stop. And then I want to keep the brake system within a safe temperature for everything. So this is the braking test rule. Basically, it's kind of vague. It says accelerate to a speed until reaching the designated area. And then basically at that area, you demonstrate that you can lock all four wheels. There's no minimum speed. You just need to show this scenario of locking all four wheels. And then we can kind of determine the ideal speed to run this test at based off some of the slides that I'll go through. All right, so this is our component layout. We have the single brake pedal that acts on both master cylinders. Between the two will be a balance bar that can change the bias between front and rear. I'll get into that a little later. There also will be a natural bias just from the piston size within the master cylinders. This will then force pressure through the lines and then go out to each wheel that clamps the caliper onto a rotor and forces the tire to slow the car down from friction on the road.
a quick point of clarification is, so the two systems are a front system and a rear system,
Front and rear.
not two like parallel
Correct,
to all
yeah.
4 points.
So we want to be able to split the bias between front and rear, because as you'll see, there's no weight basically on the rear when you're braking. So you want to have a heavy front bias. Yeah, so we touched on tire data a little bit. Our friction coefficient, we're using 1.67. The peak of the TTC data was 2.5. And like it was said earlier, this was done in a lab. So from the Millikan textbook, it recommends this 2/3 ratio to use. So our working number is 1.67 for this. And basically our max deceleration is limited by our grip. So our goal is to achieve a system capable of 1.67 Gs of deceleration. Last year, from the data we collected at SoCal Shootout, or I guess that was this year, we saw 1.3 Gs, but that actually was not locking the front wheels up. And we actually never conducted a test to lock all wheels up with the accelerometer data running. We did conduct the test just to visually like verify that we can do that, but we didn't get the data. We locked up the rears on that and not the fronts, which is not an ideal scenario because that could cause your back end to come around front, which is not what you want. You want to be able to push the fronts forwards instead of swinging 180. But yeah, basically I was just gonna say that we're gonna test this a little bit more going into winter quarter.
What went wrong there that you couldn't walk up front?
It wasn't that we couldn't, it's that we weren't trying to. We were accidentally locking the rears.
Okay.
And the bias was wrong. Part of that's because I took the balance bar out, we couldn't adjust the bias after the natural bias. Mainly because the balance bar I built was suboptimal. Yeah, so here's just a static free body diagram of the car. You got your reaction forces at the tires, our height goal of 9 inches off the ground for the center of mass. It's also 55% back from the front. And then those are just the wheelbase and the distance from the rear wheel. So basically from this, we can get our static force on each wheel, which shows a bias towards the rear in this scenario, under static scenario. And then building on this.
Is the 550 pounds with a person in it?
That is that goal number. I'm not sure if that's with the person.
Yes.
That is with the person?
It is.
Okay. Yeah, so then from this, we can calculate our weight transfer under a max braking scenario using that tire coefficient, height of the center of mass, wheelbase, and the weight. And then we get a weight transfer of 136.8 under that scenario, which you would add to the front, subtract from the rear. And then since we're slightly unsure about what our center of mass will actually be, I just kind of plotted this as a function of height of center of mass to show like the range that we're going to be in and how they kind of deviate from each other as that center of mass changes. Just to visualize how drastic this height is in this calculation. And then next we have to do is consider the aero downforce. This is actually huge because it adds a lot of weight onto the tires. It helps balance out the rear, but it also adds a lot to the front. So basically, I plotted the aero downforce as a function of velocity and added that to our static with weight transfer to produce these plots. Red is the front and then blue is the rear.
You know, just to beat that systems engineering course to death, I'd really like to see in the future, we keep saying 9 inches plus or minus what?
Yeah.
What's the absolute max that you're working to? So you can do a worst case and the rest of the design team can say, you know what, I'm not meeting this, so I'm going to do something to put a little weight lower. When do you know you got to do some redesign? So you need everybody working to a number. So
Yeah,
really,
I agree because it actually has been like a debated topic, not so much debated, but discussed a lot, this number. And no one's super sure, and we're also not sure our uncertainty on it.
well, but there's a difference between when you're designing something, you're not sure of anything, right?
Yeah.
You pick a requirement, and
Yeah.
everybody's working to make it. Sometimes you have to change the requirement because it's not achievable.
Mhm.
You get the whole team working to the same number. So it feels like you need a systems or a leadership team to say, okay, guys, we're sticking with this number. It becomes today's requirement.
Yeah.
And we're not changing it unless we absolutely have to, but make sure everybody's working to it.
Yeah, so we are sticking to this 9-inch number. I just showed the different numbers just for
I think that's good, just
Yeah.
for your sensitivity, but I haven't heard the 9 inches sound like it's a max requirement that everybody's working.
okay, that's the way I took it, is that was the max requirement. And then actually the rest of my calculations use that 9-inch. So all this is for 9 inches height.
How did you arrive at the 9 inches?
That is more of a
So it's kind of
dynamics
an
question.
estimate. We have a center of mass from our chassis, we have a center of mass from our accumulator, and a center of mass from the person sitting in the car. Those are the 3 heaviest components, and we get those, like, if we add them up, it gets to about 9 inches. It's not close because, sorry. We're not sure of that number because there's a lot of other components that go into the car, but this is how we got to 9 inches. Our original target that we started the year off at was 8. And after building more components and looking at their center of masses, we're closer to, we increased our requirement to 9.
And how will you be able to measure or assess what it is as built?
Unfortunately, the best way we can do that is in CAD. So.
Just the way you talk about it, the word requirement, you're not being real careful with the word requirement. You're talking a lot about, well, we added all this up and this is where we are. That's not a requirement. That's just your current best estimate. So
The specific requirement we have is 12 inches of center of mass. Beyond that height, the suspension becomes unstable. So that is, I suppose, our requirement. And then,
but sorry to keep interrupting, but I'm looking for a team systems thinker, because you don't want to start playing with that 12 inches. You don't want your requirement to be 12 where you're going to be okay at 11 and a half. As a team, you want some number lower than that. And it just feels loose because you're always estimating and then very willing to change your requirement. If it was a requirement, it just doesn't change. I mean, unless it just can't be done, but it absolutely could be done. So figure out a balancing the risk across all of your subsystems. Where do you want it to be? And then stick with it. And then talk about your current best estimate. We're currently thinking we're right at this. Oops, we're now thinking we're a little bit higher. But you know you need to take action if you're not meeting the thing that you all agreed to as your requirements. There's a discipline to requirements that you suggest you get more used to, because out in the world, that's what you're running
with. So then, basically, I calculated the weight bias that is towards the front from this by doing the force on the front divided by the total weight of the car as a function of velocity. And as you can see, it's pretty much the lowest it goes is 70%. Around like 20 miles an hour, it's like 71%, something like that. And from this, we can kind of get a feel for like the natural bias we want to create in our system from the master cylinders. So I created this selection matrix. The left column right here is the area options for, we want to use the Tilton 78 series because of its compact size and its mounting. I'll get into that in the next slide. But also then we did the areas of the pistons on each edge of the matrix, and then that kind of generates our biases that we can create using that formula down there. And as you can see, the best bias we can do is 72%. So that is kind of where our starting point will go to kind of bias the system off the start.
So is this the range that you can get from the part that you're eyeing?
No, this would be a, here. So that's just showing that the 71 lies in that range. But basically this would then be us choosing a 5/8 diameter piston for the front and a 1-inch diameter for the rear to just bias the system from the start without having, this bias will always be there.
Okay, so it's not adjustable?
No, so we will add adjustment in with a balance bar
Okay.
that I can get into in a little bit.
Okay, got it. So this is a fixed bias.
This is a
It's
fixed
72.
bias.
So then back on that previous one,
This one?
yeah, so that means with that fixed bias at 20 meters per second, you'll have a perfect 50-50 braking? Or what is it?
In theory, yes.
What does it logically mean?
Yes, theoretically, the force on each caliper will be the same.
Okay, so faster than that, you'll have more force on the front.
Yes,
Slower than that, slightly more on the rear.
exactly.
Okay.
Correct. And then, so from here, we're constrained on our rotor size due to, we have 10-inch wheels and we have quite a lot going on inside the hubs. So our maximum is 7.4 inches and our minimum is 7 inches. So I started the calculations using this both of them fixed at 7.4 for ease of manufacturing. That way they're just all four the same. If we warp one, if we break one, we can make another one easy. But if we wanted to, we could create another bias in the system with this size, but that's more of a variable to change if we really need to. So our plan is to manufacture our own rotors. Basically, yeah, we want to maximize the rotors in the front. And like I said, we could play around with the size on the rear, but there are other methods that are better for this than going this route right away. We are playing with the idea of fixed versus floating rotors. From what I've gathered, floating rotors are better at dissipating heat as they're not actually connected to the carrier. So it doesn't conduct the heat into the hub the same. And also you can use like dissimilar metals. You can use metal for the rotor and then a metal that's not good at conducting for the actual carrier. What's hard is they're hard to machine. We don't have experience making these. And I need to actually do some console simulations to analyze the benefit we would get from this versus fixed rotors are super easy to machine. And basically we used fixed rotors last year, had no issues. There are concerns with the aligning of the disc that also helps when it floats. But it's pretty negligible at seeing as both of our pistons move in our caliper. They squeeze from both sides. So it's not going to like force the rotor out of its path to try to push it against a stationary pad. Our calipers should center themselves based off of which one's getting more force on it. These are the calipers we're going to use. We used 4 of these last year. They're pretty good options. They're very compact to fit inside this wheel. They have 2 pistons, one on each side that moves, which is most calipers like this only have 1 moving piston, but because they have 2, it kind of like doubles the force you're allowed to put onto the rotor itself. Like I said, we own 4 from last year, but if we want to keep last year's car optional, we have to buy 4 more, which they're not super expensive. I think they're around like 150 each. So relatively not too bad, but it's something that we will have to buy if we want 2 cars.
Can I ask a question about your rotor diameter selection?
Yes.
So you said you're gonna go with the same OD, is that right?
Correct, yeah.
So what is, let's say, what does a Formula 1 car do? And what does, say, like a Porsche do, and what is a?
I'm not 100% sure, but I would think they do smaller rotors in the rears.
Every single car that we have looked at uses much larger rotors in the front and smaller in the rear. And this is something we were considering, but I think since the ratio's really close, we thought that it would be just simpler to manufacture the same parts.
You said most other cars, you mean like most other competitors in this area?
Competitors and street vehicles and racing vehicles.
I asked the question just because it's helpful to kind of know what you think the ideal solution is, and if you're going to deviate from what best practice is, have a good reason for why you're doing that.
Yeah, I guess our best reason is machinability and constraints that we're within, that our gains would be pretty marginal. So again, it's kind of early to make an exact decision. I'm a little still working through the analysis on this, but definitely is something that we are considering.
And when you say machinability, you're machining in-house, you're doing this on a manual lathe, you're doing this on?
This would probably just be a CNC. Haven't really gone through yet. Probably not manual. Yeah. Okay, yeah, so touching on the calipers, there are 2 pad options. Actually, the second pad option was released 1 month before competition last year. So last year at CDR, we only had 1 pad option. So this is exciting as we have doubled our options here. So another bias that can be created is by using the less, I guess, worse pads for the rears that have a lower friction coefficient and better pads for the front. Basically this one, it changes a lot with temperature until it gets to a hot temperature and then it just stays still. Whereas that one doesn't vary a whole lot between the cold and hot temperatures. So part of the brake test is you kind of run it on cold tires and cold brakes. So you want to have like a high, and you don't get to put heat into it before you get to run the brake test. And so you want to start with a high friction coefficient. You do get to do multiple runs though. It's not like one attempt and you're done.
The purple one was the new one?
Purple was the old one.
Okay.
And then BP, there's a lot of lines on this plot. I just took this from their website, but it's this yellow one right here.
So you'd want to, because the purple changes 30-some% over range.
Exactly, yeah.
The
It's
other
less,
one's much
the other one's super
10%
stable.
or something.
Yeah.
20%.
So how'd you end up with the purple one last year?
What was that?
How'd you select the purple one for last year's car?
That was the only option last year. And then they came out with the BP 28, actually 1 month before comp, and I ended up buying them and putting them on the fronts for comp. And I just said, let's just do this. Yeah, so then we can get into our torque required per axle to stop the vehicle, which again, red is the front and then blue is the rear. Around that 20 miles an hour range, it's like 450. And you can see how it kind of ramps up as the speed goes up, which is not super concerning because we're not terribly concerned with locking the wheels up at 60 miles an hour. In fact, I think it would kind of be bad if you're going 60 and you had a jump scare and you pushed on the pedal as hard as you could and you immediately locked up. So it might be a little better to shy away from that peak and kind of make them lock up more in the mid-range of our velocity. And then I get into some of the dynamics of the system. These are just a bunch of constants that will be in some of the equations that I'll be presenting here. I'm going to skip going through them. Just if you have questions about any of them, feel free to ask.
Well, I do get nervous about your assumption on what's the best, but I realize, I'm pretty sure I heard the requirements don't state any velocity.
No, there's no minimum velocity. And part of that is how the aero package plays into the downforce. And that as you go faster, there's more normal force on the wheels, which makes it harder to lock up. So it's kind of like a interesting middle point that you want to hit.
Well, so it sounds like you have some flexibility in choosing how you want to go about that. What do you think the intent is on the competition side for having the lockup requirement?
Just to be able to demonstrate that your brakes are working effectively. Like if you can't lock your wheels, then there's kind of an issue with how you design your system.
I mean, other types of ways people look at this is like a stopping distance, minimum stopping distance.
Yeah. That's without locking though. That's with, for that you would want to keep like no slip at all for that, which that's not one of the tests actually, or it's not one of the competitions. This is just like a past technical inspection for the brake lockup tests.
Is it a design driver? I mean, you're designing to this particular
Yes.
lockup requirement.
Yes,
How does
because
that
if we
impact
don't
the rest of the performance?
pass this, we can't compete.
Sounds
So
like you have a fair bit of latitude though, of how you want to approach it, like go real slow and demonstrate a lockup. or go
exactly,
fast.
yeah. So that's why I listed that rule. It's because it's very vague. Just says like for the internal combustion cars, it lists a minimum speed of I think 15 miles an hour. But for the electric vehicles, it lists no speed. It's pretty vague. So a rules clarification might be good on it. But from last year at comp, viewing most of the other cars, they did this approximately 20 miles an hour range.
I guess I don't want to see you change anything. I just wish I better understood real world ramifications. If you're going X miles an hour, is it true you don't want the wheels to lock up? Or are there a bunch of cases where you just assume lock them all up and just control it because that can stop you even shorter?
As soon as you lock up, it'll actually take longer to stop because you're switching from a static friction coefficient to a dynamic or a kinematic friction coefficient.
Yeah.
So you'll actually, which is always lower than static.
Okay.
So you'll actually slide further and stop longer than if you have traction.
With that answer, with that explanation, I'm fine with.
Okay.
Well, there's one other way you could look at that, which is you know, from like a factor of safety perspective. Lockup, you don't, for maximum stopping, you'd never want a lockup,
Exactly,
but your driver might want the control authority to have that option, and it's through his brake
through his
modulation.
field, yeah.
He has the option.
Yeah, so that is also part of it is driver feel, what driver wants, their sensitivity feeling. Which I am one of the drivers, and so I agree with that. I guess with testing, I can kind of figure out how that is.
Yeah, I haven't missed this, but is the torque to lockup,
Correct.
but is it with cold tires or are your calculations with cold tires or?
I used the friction coefficient for the tire, I take as a constant of 2/3 of the peak friction coefficient. That was from the TCC data,
Okay, so
but then the pad friction coefficient, I used kind of just like I use this one, I listed 0.475, but I think I used 0.45 in my calculation. Just because it starts at 0.4 and it goes up to about 0.475 is the peak. So I listed that peak there when I wrote average. So that is a little bit off, but
What if you look at it with the worst case, like?
at
everything's-
0.4.
Yeah, everything's cold and you go out and.
Yeah, so
runs in front of you.
I put all these equations into a MATLAB script and I can just change the variables and see how it affects everything.
Okay. And then back to the point of, personal feel or whatever, because braking is one of those things that.
Yeah.
Drivers really have their own opinions on, like, are you going to, find that every possible condition meets the requirements and then give yourselves like, I'm gonna put the purple in the back today, or no, I'm gonna go yellow in both, or
We could do that.
adjust the bias for A or B.
That would be a very optimized design,
Yeah.
which would be impressive if we were to get to that point. If we could put that much testing into the car and have those decisions for each driver, that would be amazing. But I'm not super hopeful we'll get there.
Go
I
for
do
one
want to get there, don't get me wrong, I want to get there, but
Right.
that would be the ultimate goal. Also part of that is the so I'll get into it a little bit. I think I went through this slide, yes. Yeah, so then from here, I rearranged this torque calculation, which I solved for in that plot that you saw per axle, and then I solved for the pedal ratio that we're gonna need out of our pedal. Basically, I don't know if you guys are looking at this or if you want me to skip through to the next slide.
It might be nice to have a sentence for explaining to me, like I'm a 5-year-old, like, this chart tells me how big of this to make or whatever.
Okay, gotcha,
like,
gotcha, yeah.
Maybe
Yeah.
the judges don't
So-
need that, but for.
So
5-year-olds,
I solved for torque here, and then I drove this torque formula, and then I rearranged it to solve for the pedal ratio I'm gonna need out of the pedal that I'm building. And basically, this is the pedal ratio here as a function of velocity to lock the wheels up at, I think the torque I chose was at that 20 miles an hour. And as you can see, so this design is not what it's gonna look like. As you can see, our mechanical advantage is really small on that. So, and you can see the pedal ratio we need is at 20 miles an hour is approximately like 3.5. So, going off of this formula up here, it's the total length of the pedal divided by your mechanical advantage. That's your pedal ratio, which it will change with the arc of the pedal. But I'm just factoring in the like instantaneous pedal ratio for now before I get into the analysis of how it changes with arc. So that will be redesigned. This was just kind of for a picture. I haven't gotten to that design part yet.
Are those the master cylinders also?
Correct.
Okay.
And they actually are oriented upside down in this picture. They should be 180 that way.
The feeds
Yeah,
going
around the
out.
Z axis,
Yeah.
with the feeds going out.
Yeah.
Good. So yeah, then we can implement into basically right here is the balance bar. This is adjustable. What it does is it changes your moment from that center point onto the front and rear master cylinders, which changes how much force goes into each with the single input force of the driver. which we're estimating to be 100 pounds. I've tested that with scales that I put it against a wall, sat in a chair and pushed as hard as I could. I got to 120. I talked to judges last year. They said a good estimate was 100 pounds. Because there's other things that play into that. Like as soon as you start slowing down, your body weight goes into it. So 100 pounds, I think is safe. A safe call on that number. Oh wait. Is he going backwards? Yeah, so this is the balance bar. Last year I tried to build one of these. I failed. I did not do FEA on this middle bar, and I made it too thin, and it was bending under that 100-pound force. So then in the last ditch effort, I removed it, took it to the hole, and just put a fixed bar in there of a bigger diameter that ended up working. And so that basically that made our system kind of, for a GR24, stuck at the natural bias. So this year, I'm gonna buy one off the shelf. They're like $70, and I spent like I don't know, half a year trying to build this thing. So save myself the headache. I learned a lot about it, but I'm gonna buy one off the shelf. Basically what you do is you tap a hole in your pedal, weld this sleeve in, and then there's a spherical bearing in here that slides in, and it's kind of free to move around. It also moves this way, but then fixes in place with your actual master cylinders and then changes that moment. And over here you can see basically your max adjustment from the natural bias is to go 60% or 60% 35 from your 50-50 point. That original 50-50 point would be your natural bias. So we can go even further towards the front if we need to. Brake lines.
What kind of force are those rated for?
Which ones? The balance bars?
The balance bar off the shelf.
There's a rule, I think, that your brake pedal has to withstand 2,000 newtons of force, but the test it's subjected to is the judge putting his max force into it. So as long as it doesn't yield under a judge putting their max force into it, then it passes the 2,000 newtons rule.
No,
What is this rated for?
Yeah, because I want to have some sense for what kind of margin you have. I'm
Yeah,
assuming it's a lot, but I just wonder, do we know what that thing is spec'd for?
I do not, but I'm sure I could contact this company. Tilton is in Buellton, just right up the road. So I'm sure they would be, I'm not sure. I'm hoping that they would be willing to tell me that info.
It seems like a key parameter to their.
Yeah, exactly, because that was my failure point last year.
Wasn't that what the 100 pounds was, or was that 100?
That was 100 pounds times, that was 100 pounds times your pedal ratio.
Okay.
So however big your pedal ratio is going to be the actual force going into that bar.
Okay.
And then that force gets divided between the two master cylinders based off of another ratio going horizontally.
So it sounds like you really understand it. It's just nail it by knowing that
Yeah.
this thing is spec capable for your actual input.
Correct, yes. So I do need to get that number.
How will you test or assess that you've done it right? And performed
You
as
do a
well?
brake test. So you try to lock all the wheels, and actually the ideal scenario is to lock your front wheels momentarily before your rears. Like if you can get them at the same exact time, that's amazing. But theoretically, you want the fronts to go a little bit first, because if your rears lock up first, say you're in a corner and you slam on the brakes and your rears lock up, you're going to 180. Versus if your fronts lock up, you're going to push forwards. So
I was curious, is there a kind of a laboratory test you think you could do to, validate that you built it?
in terms of like yielding of the components, or in terms of
No, I was thinking about
bias?
your bias.
Just testing the car. That's really what it comes down to.
Sorry, we do have pressure sensors.
That's kind of what I was getting at.
Yeah.
We
Pressure
have
sensors on the hydraulic lines or load cells.
we do have pressure sensors built into the hydraulic lines, but those are going to be once we build the lines in the car. The lines are custom built. Most of them are actually. I'll just go to the next slide. That's what I was going to talk about, anyways.
If the brake apparatus is kind of a unit that can be built outside of the car, could you just install the pressure sensors right into the masters?
For lab testing?
Yes.
Yes, you could. Yeah, you could, and then you could analyze your bias off of your pressures.
It's definitely worth doing, it's design points.
Yeah, it'd be pretty easy, and then just make a mock-up mount for our pedal box. Yeah, I mean, yeah, we totally can do that. I just never really thought about it.
It might be easier, else that way you probably can pre-bleed a bunch of it,
Exactly, yeah.
Benchmark your, masters.
So another part of that, also right here, I wanna, if we have the budget, I wanna do quick disconnects on all of these line connectors. Basically the way they work is they're spring valves, so that you push them together and then it opens up the valve and basically seals it at the same time. We had one on the car last year because we had a removable rear manifold is called, which was our whole rear wheel and shock assembly. And that's how we took the battery in and out last year. So that had to come off regularly, and I didn't want to bleed the brakes every time. So I added one right there, and it was 10 seconds to unclip, 10 seconds put back, and there was no issues with air getting into the lines and causing pressure weakness within the pedal. But yeah, basically for the majority of the system, we're going to use these hard lines made out of, it's like a nickel copper, I think. Last year, a company out of Boston donated a bunch of that line to us. We have some left over. And so if we need more, I'll probably be in contact with him and see if he'd be interested in doing a little bit more for us. And then basically what you do is that's just tubing. You get a flaring tool where you flare the ends, or you put the fittings on first, then flare the ends. And then you have your brake lines that can connect into these flex lines, which go out to each wheel component so that the wheels can move without bending your hard lines. The benefit of the hard lines is they don't flex under pressure. So you have a more consistent braking feel, whereas the flex lines, they are wrapped in stainless steel. So it does do a good job of that, but there is still some bulging under like maximum braking efforts. Yeah.
So I think I remember this issue about having to break up something to get the battery in and out from last year.
Yeah.
Is that design aspect going to be there in this year's car?
It will be touched on later. It's
Short answer, no.
Okay, good. Yeah, having to disassemble a safety critical system every time
Yeah,
seems like an unnecessary risk.
agreed. But the quick disconnect, I was surprised at how well it worked. So I want to do that for all of our fittings this year so that we can have pre-bled calipers if we need to throw one on real quick at home. This is a quick line pressure calculation. The lines are rated to 1200 PSI at a constant pressure, 1500 peak. And I calculated we're going to be seeing about 234 in the front, which gives us a safety factor of 5.1. So not super concerned there. Last year, we didn't see any concerns with what we had going on. I think this calculation might be for a smaller pedal ratio too, which now our pedal ratio is going to be going higher to like 4. So that number will increase, but we still have a lot of room to work here.
So you mentioned the pressure ratings for the lines. What are the pressure ratings for the other system, other components?
The lines are the weakest. That's why I highlighted them. Willwood tells me all of their components are rated to this. And if I were to predict a failure anywhere, it would be a line, and particularly like one of where the fittings attaches onto it.
Does that include the quick disconnects?
The quick disconnects were made by Racetronics. So actually I did not get that value, which I probably should. Yeah, so then moving into the pedals, which is kind of what this whole thing has led up to, which is still very much a work in progress, but I'll just present what I have so far. So the pedal constraints are, you guys saw Percy earlier, the big model we have. So between the circle of his hips and the pedal face, there has to be 915 millimeters, which is actually quite a long distance. Last year, that's why we had to take the seat out, is because we did not meet that requirement. So we ran just a sheet metal seat instead of having an insert, which actually solved it and made it like a few millimeters of margin safe. So this year, that was my main concern with the pedals. At full travel, they have to be an inch away, 25 millimeters away from the front. Any chassis member in the front, anything that attaches up there. The brake needs to have an over travel switch so that if the system becomes depressurized, the car shuts off. The accelerator has to operate an accelerator position sensor. And basically, also the vehicle has to, or this, sorry, I have this bullet point in the wrong order. So to measure the, okay. So there's like a brake system check that you have to go through before the car can start. This is, I'm sure electronics will go into it a little more, but basically you have to activate the braking system before you can like enter the ready to drive mode. Last year we tried to use an encoder for it, but per the rules it says we can use these pressure sensors. So that is the route that we want to go. This is our preliminary pedal box design. This is the throttle we used last year, which I didn't really see any issues. We 3D printed that mount for the accelerator position sensor, and it actually worked really well. So I think we're going to stay with that same design. We already have it. That was actually bought off the shelf. So we can just buy another. It was like $100. And then we're going to redesign the pedal. Again, that is not going to be the geometry. There is no mechanical advantage in that geometry. So still working on that. I just touched on a few of these things. We're trying to angle the master cylinders like that to save space. Last year we did them horizontal, which caused the pedal box to be really long and took up a lot of space in the front of the car. So we're trying to do this horizontal scenario to be able to kind of shorten everything, reduce weight of all the chassis members and everything. The mounting, we wanted to drill into the chassis members, the square bars in the front, but upon completion of the chassis, they're actually angled in like this. And so we have to come up with a solution for mounting because it won't be adjustable if they're angled because the distance is always going to change unless we have the mount points on slots that can slide in and out like this. So still working there. Our space claim as of now for the front is 6 inches this way and 11 inches tall. It was originally 9 inches, but no one has claimed any space above us. So I claimed an extra 2 inches. But yeah, overall, I want to reduce the weight. Last year we did no weight optimization. It was super heavy. The pedal faces were uneven because of the super long master cylinder, so it's kind of weird for the driver. And it took a really long time to install and adjust the position. So I want to streamline that whole process.
I'm glad to hear you guys are managing volumes well enough that somebody can go out and claim volume within the vehicle. That's a good practice.
Yeah, there is. Volume is such a high commodity on the vehicle that it's kind of like where we all start is like, what is our working space? But yeah, so the BSE brake system encoder. Last year we used a rotational potentiometer. It needed a really high resolution to function because the brake pedal doesn't travel much. We had a lot of troubles implementing that. We ended up switching to a linear potentiometer that was actually designed for a suspension component. That was way overpriced, way too big. It works, but it was like a last-ditch effort. This year, we want to be able to utilize the pressure sensors. It is rule compliant. I put the rule there that states it. BOTS is brake over travel switch. Last year we had a really big push type, single pole, single throw switch that basically would stay down when you would lock it or when you would actuate it. This year I want to switch to a flip type. It saves a lot of space and kind of will help us reduce that whole pedal box size. The throttle sensor, basically a rotational potentiometer. I'm sure the controls will talk on this more. My job mainly is to incorporate space for it and mount it. Last year's mounting scheme worked great. I don't see any changes unless controls tells me some changes they want. So I want to go ahead and use a similar mounting scheme this year. And that's it. And then we're supposed to do lunch right after this. Any final questions?
So just make sure that chassis integration gets done. There's like.
Yeah. because we can't let that lag. Yeah, that was a big thing last year, is the chassis integration lagged, and then we basically got fixed with a single pedal position.
So when you guys share this with the judges, are you talking, or is it just here's all the documents and they read?
I think one person talks.
Okay,
It's not like we all get up and talk like this. It's like one person is kind of responsible for the design. We also submit design documents.
okay. Cause some feedback for this is, you had a lot of good words and commentary to support the stuff on the slides.
Yeah,
But the slides need more commentary, I felt like.
if you were to read them.
Yeah, it's
Yeah.
like, out of context, it's just a slide with an equation, and then an equation, and then an equation.
Yeah.
And if you connect them and say like, I do this calculation so that I know this, and then with that, I know this, and then, so it's like telling a story slide to slide
Gotcha.
to paint the picture, I think.
Yeah,
You
I
did
guess
that
it's
really
more-
well vocally, but
Yeah.
I think the slides in isolation wouldn't necessarily tell the same story.
I guess I more catered it because I knew I was going to deliver it.
Yeah.
But if I were knowing that I was just going to submit it, I would
Yeah,
make it easier to
consider
read.
the audience, yeah, for the
And
judges.
it's also a good suggestion, period, though, no matter, even if you are gonna be able to talk to your slides. It's
Right.
still helpful, because people might have said it, they wanna go back and reconfirm it, read it.
Gotcha.
I think one thing to add to that is, really helpful to say, kind of, what is the main takeaway of the slide? You're gonna take away just one thing, why are we doing this? And they've got a real clear, visible.
Gotcha. All right, thank you.
Yeah.